Okay, so hello again, and we're gonna start the second part of the lectures. This time we're gonna discuss this module. We're gonna talk about various machine learning methods and graphs. Today we'll start with sort of the most straightforward method. We'll talk about node classification, but I'll discuss in a second things in more details. So when you think about machine learning methods, there are a few things you could try to predict when you're on a graph, right? On a graph's structure. So one thing is, for example, you can think of like node classification on node type of regression. So when you have particular attributes associated with nodes, and you want to infer the values for the attributes for the unknown nodes. In the simplest settings for, say, social networks, you can think of, for example, gender, or if you think about, again, social network settings, you can think about, age as something you can infer, or income you can infer, etc., etc. Of course, you can do much more interesting problems in the networks that differ from social networks. Another problem you can think of, have nodes. There are also links, right? And you can think about the problem of link prediction. That is try to predict the links, try to predict, for example, when you have a given graph, try to predict links that are missing for whatever reason, and that may be, for example, they're hidden from you, and you try to discover hidden connections in between people, or if you have a graph that evolves in time, that might actually predict that there will be a connection between those two nodes. You can also use this, and say Facebook or LinkedIn uses that as a friend suggestion service, which is in fact, it's just a link prediction, right? So which two nodes has to be connected, and so that can predict your friends. Another machine learning typical problem is a community detection problem, right? With community detection, we have done that already. That's really, clustering problem, right, for the graph. Then you can think of graph classification, where you actually take different graphs and you actually work on classifying graphs themselves, right? Because graphs consist of nodes and links, and they have certain structure, so they're objects, and you can classify graphs themselves. That makes that type of setup, that problem makes sense a lot in structural chemistry, trying to predict the structure of small molecules, and that's extremely important for drug discovery. We're going to talk about some of those methods. We'll start talking about those methods from the point of view of sort of classical machine learning, where we look into features, and we build models. Sort of, we're going to use traditional machine learning methods. Think about like SVMs, or or trees, or anything else, and we're going to build features for that, right, to use with them. Later on, part of the lectures will be about sort of a more advanced approach, which is graph embedding or graph neural networks, where we'll start thinking about looking for new representations for the graphs. That actually includes, of course, the nodes and the connections, right, the links, but representation is mostly sort of vector form representation that is derived through the neural networks. So that's what we're also going to do in this module. But today we're going to talk about node classification problem, and the idea is quite straightforward. So you do have labels on some of the nodes in the graph, and you do have edges, you have connections, and you want to predict labels on the nodes that are not labeled. And let's say on this slide you have two positive nodes, two negative nodes, and the question is what value or either plus or minus will be on other nodes. And for some nodes, it's sort of more or less obvious, like node number 9 or node number 3, but then there are questions. So what to do with node 4 or node 5? So it's actually the question of extending labeling from the subset of nodes to the rest of the node of the nodes on the graph, and those labels can be either class, right? Particular class, belonging to a particular class. It could be probability to belong to a particular class, or it can be a regression problem when we try to find numerical value associated with a node. There are a lot of names that associated with this type of problem. There is network data, network classification, there is structured inference, relational learning. This is all more or less describes the same approach of actually trying to make inference based on the data that has internal relations. So now, if you think about it, like sort of from a big picture point of view, structure, those connections, those connectivity patterns can help identify the values on the edges only if there is some sort of correlation between connected nodes, right? Because otherwise, if there is no correlation between connected nodes, the values of connected nodes, then there is really no help out of structure. Now, in social networks, that actually works because we know that it usually has this assortative mixing property, sort of bias in favor of connecting between nodes with similar properties, right? Similar characteristics. And so we talked about like homophily, which means, the nodes with similar characteristics are connected, like say political views or any other characteristic. But we also talked about, influence, possibility of influence, and then, connection can cause, cause people change their opinions. And so there is an influence. And if you can build this, you can actually use these methods on the sort of actual physical networks, or you can actually build networks, create similarity networks, and then use them and use the models on those networks, right? For example, you can build a induced network from an image where every pixel is a node, and you connect pixels if they're either next to each other or there is some, for example, the color scale is the same. So, the general problem setup is that we have a graph of nodes, and there are some nodes are labeled and some unlabeled, right? So all nodes just split into two groups, labeled and unlabeled. And the labeled nodes have labels, and those labels can be either categorical or numerical. And there are some nodes that are not labeled. And the task is to find those unlabeled. So it's V sub L and V sub U. So for every node, we can actually, compute features. The node can have all kinds of attributes, and we can actually calculate those local features, sort of the feature by the node. But we are mostly interested right now in how we can use link features, right? So the features that come from the connectivity pattern, the features that come from nearest neighbors, right? Attributes of the neighbors. And then you can think about this sort of as having a feature design matrix, the same way as always in machine learning problems, that has part of the features are sort of link features, and part of the features that are related to other attributes. Now, again, right now we're going to be focusing on the link features simply because, again, we want to, this class is about networks, so we want to understand how those networks helps us. Now, sort of brute force method, the easiest method of the classification is, is the following. Actually, guys, what do you think the easiest way to solve this classification problem, to propagate labels across the graph? What would be the easiest way, sort of the most intuitive? Well, I mean, think about this. If you have some nodes that are labeled, some unlabeled, let's say, you're looking for an age of a person, and the age is not showing on his Facebook profile, how can you guess his age or her age?
Maybe the average of the neighbors of this node.
For example, right? So that's going to be, if we assume that, people usually become friends with their age group, right? You can either just take like almost, one neighbor and check up that age, or, to be more consistent, take an average, right? And, if you think about more, that's what you do if you have that's right. I mean, that's the easiest way to do it. And actually that works in many cases. Now, it's just not going to work easily if your neighbors are also not labeled, right? Then there's a question, so what to do? And that's what we're going to address in a second. But if you think about this sort of more in more general form, and we think about not only about the numerical values, but labels, class labels, you can actually build probabilistic type of classifier. And there's really, sort of two ways of doing it. One way is, yes, you can actually just take neighbors, probability of the neighbors belonging to a particular class, and say average them out. And when you sum over A and J, that's sum of the neighbors. Or if you think about more in sort of bias kind of view, naive bias approach, it's also going over the nearest neighbors, and the probability of the node depends on the probability of the neighbor. So probability of the node belonging to a particular class depends on the probability of the neighbor belonging to that class, and then you multiply those probabilities, then you'll be consistent with sort of probabilistic approach. So the question then is like, okay, what do we do if we have a nodes, like on this slide, there is node Y, and that node does not have neighbors that are labeled. And so then the question is, okay, what are we going to do with this guy if there is no labeled values next to it? So in this case, you probably can do sort of iterative classification. For example, here on this slide, again, their XYZ values are not known, and their blue nodes have values 18. So in the first step, we predict the value of the node X, and on the second step, we propagate the value from the node X to the node Y. All right. So I mean, it's also very, very much intuitive thing, and there's sort of not a big science in here. All right. I want to talk today about the very special approach, which makes the sort of graph methods different. I want to talk about what's called semi-supervised learning, because so as I said before, we have partially labeled data set, and we want to spread those labels, and we're going to use some very, very, very graph-specific algorithms. Again, there are multiple ways of doing this. You can actually build features and use traditional machine learning algorithms. We're going to talk about a way which is very specific, very particular to graphs. So one of the very interesting ways is a random walk method. So it's a graph-based way because you need to have a graph to have a random walk. Now, the key to this method is the following. The key idea is that we're going to look at the random walk with absorbing states. Now, do you guys remember we talked about absorbing states when we talked about PageRank? Can you remind me what is absorbing state in a graph? If we have a directed graph, what's absorbing state?
A leaf?
Well, yeah, it's a leaf node. It's, let's say, if I have a directed graph, and we have it this way, and then there is a sink. It's actually called a sink node, right? So if you start your random walk, and you walk around, you can walk around, you can walk around, but after you get to this node, you're stuck, right? This node is absorbing. And to be consistent with, we talked about this before, also to be consistent to write this correctly with as a Markov process, for the random walk, it's actually the good thing to do is to have this self loop. So the random walk never stops. So on every step, you can actually, on every sort of count, you can make a step, but then you never leave this node, right? It's sort of virtual step back to this node. So again, you walk around. When you get to this node, you're stuck there, okay? So the key of the method that we're going to consider is that we were going to consider a random walk where labeled nodes will be absorbing states. So if we have a graph and you can walk around it, whenever, and there are some nodes that are, this one is labeled. Let's say this is unlabeled. This is unlabeled. Let's say this is also labeled, unlabeled. And let's say you walk from here randomly to here, and then you step here, and that's labeled node, and that's considered absorbing, and your walk is done, right? Or you start, say, from here, you get here, you get here, then you get here, and it's also labeled node. It's absorbed, you're done, right? Okay, so and here is the idea. Here is the sort of the main assumption of the model. So the probability for a particular node to have label C is given by the following formula. So the probability for the node to have a label is given by the following formula. We're going to sum over all labeled states over all absorbed states, and of all the walks that ends up on those absorbed states. So what this pretty much says is the following. We start with at some node, let's say we have, let me try to do it again. Say we have a graph. Have some graph. And in this graph, we have, say, this state, which is labeled, and it has blue label. And let's take this state that is labeled and has red label. And what we're gonna do is we're gonna start random walks. And let's say we start random walk. Let me take it. Let's do it this way. We start random walk here. Let's say it moved here. It got here. Okay, it absorbed. Then we start random walk here. It got here. Then it got here. It got absorbed. This time it absorbed by the red node. This time it was absorbed by a green node. So the probability of this node to have label C is proportional to the number of, literally to the probability to get to the probability of being absorbed times the labeled on the node that where the walk has been absorbed, right? So I want to understand the probability of this node to have red label. Okay, I calculate all the random walks that end up on the red nodes, and that's where they're absorbed. If I want to calculate the probability of this node to have green label, then I calculate all the random walks that end up on the green node, all those probabilities times the probability of that node to have green label, which is 1, and add this up. Okay, so literally what's happening is you're considering random walks on the graph, and for each starting point there might be multiple random walks, and they hit different absorbing states, and you just calculate which absorbing states they hit and how often. And then depending on which absorbing states dominates, that will define the label of the node itself from which the random walk started. Does this make sense? So the label of the node from which the walk starts is determined by the labels of the nodes where by absorbing nodes. And you just literally calculate the probability that the walk ends up there. If you think about this for a second, let's say there is this node, and then these are direct connections, and here is 3 nodes, and let's say this is a green node, it's labeled green, this is a green node labeled green, this is a green node labeled green. And then we simulate, we start random walk from here, random walk, one step, it's absorbed, another random walk, it absorbed, another random walk, it absorbed, another random walk, it absorbed. So pretty much all the random walks that starts at this node getting absorbed on green nodes. Then this sum will calculate into 1, and the probability for the green node, the probability of the central node to have green label is 1. If we somewhere there have red label, it will never reach it, and so the red label will not affect it. But if, for example, on the nearest neighbors there is no, say, there is no direct, let's say, let me do it this way. There is green label, say, and there is a green label here, and then there is a red label here, and we consider random walks starting from this node. Yeah, this random walk will end up on this green side, and it will contribute it to the probability of it being green. And this random walk will end up and get absorbed on the red and will contribute to the probability of being red. And this random walk will get absorbed on the green and also contribute to the probability of being green. So with this picture, more likely this will get, with a high probability, will get labeled green. So that's the logic. All right, guys, again, I'll stop for a sec. Does this make sense as a concept? All right. Well, I assume it does. So okay. So then the rest is really just sort of mathematical technique, how you make this work, right? When we want to calculate the probabilities, if we have Pij is one-step probability, so it is the same probability transition matrix as as what we looked into when we did PageRank. Then Pij to infinity, that is means infinite number of steps, or as many as needed for the walk to get absorbed. And so in a matrix form, you can write it the following way. You can write nodes labeled, unlabeled, and you can calculate sort of finite state as split the nodes into labeled nodes and unlabeled nodes, right? And calculate transition from labeled to unlabeled by taking the transition matrix, taking the original state, also split into a group of labeled and group of unlabeled nodes, right? And multiply it by transition matrix. And you multiply it once, it's one step, you multiply it twice, 2 steps, you multiply it 3 times, 3 steps, and you multiply it, infinite number of times. It just means there is a walk until, walking forever until it gets absorbed. Okay. So then, like as we discussed, we're looking at the random walk matrix. This is pretty much almost that sort of PageRank matrix, except for we don't do sort of corrections as in PageRank, but the matrix come from the fact that this is your adjacency matrix, and this is normalization diagonal -1, which actually takes into account the fact that when you at the node you have several neighbors, the probability to move along one of the edges is inversely proportional to the node degree. Okay. Now, when we consider a random walk with absorbing states, there are really sort of 4 different submatrices you can think of. You can think of going from the labeled node to labeled node, right? You can go from labeled to unlabeled node, from unlabeled to unlabeled, and you can go from unlabeled to labeled, right? That's all possible transitions in general. But since labeled nodes, remember, labeled nodes, they are absorbing nodes, there is no way to get from labeled to unlabeled, because, you know, the moment somebody gets onto the labeled node, it never leaves. So the entire matrix, and again, guys, this is, though it's written 4 by 4, but you should think about this as a sort of big matrix that's split into 4 quadrants. And here we have all the labeled. There are a bunch of values for transitioning from labeled to labeled, right? This is labeled to unlabeled, unlabeled to labeled, and unlabeled to unlabeled. So unlabeled to unlabeled, these are just from one node to another when there is no labels. And so it can easily transition. And so here we always have values. From unlabeled to labeled, this is this last step from here to the labeled node. And so we always have values here. From labeled to unlabeled, you cannot go because, you know, whenever you hear, there is no way back. So that transition is not possible. And so all the values in that quadrant are 0 from labeled to unlabeled. And when you go from labeled to labeled, remember the only transition for labeled to labeled is on the same node, right? It's not going anywhere. But in order for this for Markov chain work, you need to have those transitions, right? Self loops, and that's why here it's ones on the diagonal, which means self transitions, and zeros everywhere. Okay. And so you can write this as a block matrix as shown here. This corresponds to set of nodes that are labeled. That corresponds to transition between sets of nodes that are unlabeled. So again, if we look at this, these guys are all labeled nodes. These guys are all unlabeled nodes, right? And here it's all labeled nodes, all unlabeled nodes. So we take all the nodes in the graph and, you know, sort them, take part of it which are labeled, put them together, right, in the matrix, and part that unlabeled, group them together in the matrix. And so those are the pieces. All right. Now, what's interesting, if we take this matrix, and this is one-step transition matrix. If we look into infinite walk, it is p to the power infinity, which means many, many steps. Or, you know, p to the power infinity, it is one step, time another step, time another transition, time another transition, and so on. So we can actually take this matrix and multiply it by itself, right? Multiply it t times and then take t to infinity. Well, one can show, I mean, obviously, if you take diagonal matrix multiplied by itself, you know, it's going to be the diagonal matrix itself. If you take 0 and you multiply again matrices through matrices, that remains 0. What's interesting, that this value, when you take it to infinity, will also go to 0, because you know, it's eventually, when you take the random walk forever, everything get absorbed. And this sum, one can show, I'm not going to do it now, but you can look up in the book, you can show that it converges to this value, where this one is transition probability matrix from unlabeled to unlabeled, and this is from unlabeled to labeled. And so you can actually numerically show what's going to happen here. Okay. Why am I doing all this? Well, because then it's actually very easy to see the result. So if I think about this random walk and look into this matrix equation, so on the right-hand side, I have initial values of labeled nodes and an initial value of unlabeled nodes. This, you can think about the probability of it having certain label. And this is, sort of final value after the algorithm works through it. You can see by looking at this matrix equation that, of course, labeled values will preserve their labels as a result of this random walk. Because if you start with the labeled node, you kind of end up on that same labeled node, and so the labeled node will be assigned the same value. And if you start on unlabeled node, you will walk until you get absorbed by a labeled node, and then the probability of that unlabeled node can be calculated through the transition probability matrices in this way, right? So, and this encodes the connectivity and the walks in between unlabeled and labeled nodes, and this encodes walk in between unlabeled nodes. And so one can show that this is, that's non-singular, this matrix, and you can actually just calculate this number. So bottom line, I have described you the sort of the logic, right, and the method, and you can just simulate this, like literally start random walks, see where they get absorbed, calculate how frequently they get absorbed in which nodes, count where they started, and assign those frequencies of absorptions to the nodes where it started from. Or you can trust linear algebra and just take this matrix and invert it and do this multiplication. It will calculate probabilities for you automatically based on what we saw on the previous slides. Now, inverting matrix may be not a great idea, but running sort of random walks also not sort of the best way to use computer time. So there is this algorithm proposed by Zhu in 2002 that actually kind of simulates this without actually simulating it by solving the equation without simulating it by iterative process. So the idea is you just take literally this matrix equation and you just keep iterating it, right? You just go step after step after step, just multiplying this matrix by the right-hand side and update right-hand side. And if you do this, as we have seen, it guarantees to converge to this value, right? And pretty much the only thing you need to do is you compute diagonal, you compute the transition probability transition matrix for your graph by normalizing your adjacency matrix. You initialize the nodes to carry the labels that you have, and you just iterate. And so eventually it will converge, and the nodes will carry, there will be the probability for nodes to have certain labels, depending on labels on the graph. Obviously, in this case, you can have sort of as many type of labels, right, as you want, right, as many classes as you want in this type of approach. Now, this approach actually originated, and there are many more approaches similar to this that has been proposed later. For example, one of them has slightly better convergence properties, and instead of just sort of traditional random walk that I described to, this uses slightly different random walk, slightly different matrix, and slightly different steps that affects the convergence of the algorithms. But the idea is very, very, the idea is pretty much the same. So this is a sort of very, very graph specific algorithm, because this algorithm is designed to work on graph and explicitly uses graph structure. Now, there is slightly different angle to all this that, and it's easier to understand if we consider regression type of problem on a graph. Think about it this way. For me, there is this always, this sort of cartoon is helpful. Think about sort of, say, chain, right? And what I'm going to draw now is, let's say there is a function, there is some values, right, that are assigned to some of the nodes, right? So the sum of the nodes are labeled, and let's say these are the labels. And so what we need to do is we need to, predict the value on these nodes, right? Now, if you look at this as a one-dimensional problem, this is no different from your traditional, say, regression, right? You can say, okay, well, how do I find the value here? I can take the value on the neighbors, right? And let's say take an average, values on the neighbors, and take an average. Can we do it? Yes, of course. Now you risk, somehow lose a little bit of overall picture if you do this. But let's say, or if the value, oops, I erased too much. I'll draw it again. Or if the values, say, known right here and right here, and you want to predict them, and let's say here, maybe you want to do, run some smooth function in between in those nodes, and that's your values. That's a prediction on those nodes. So when it's 2D, when it's 1D, it's very easy. It's actually traditional approach, right? Now, if we have, instead of 1D, we have a 2D structure, right? Very nice regular structure. Then it is always, and let's say you can think about building a regression type of function and interpolating in between those nodes, and that will be your answer. And that's correct, right? That's the right thing. Now, the only question is, if instead of this regular grid, you have some, graph structure, which is, different from regular, right? So how would you do that? And the answer is actually you do it exactly the same way as we just discussed. Now, if you think about this, if you remember how we calculate regressions, you'd usually try to take a function, calculate the difference between the actual function and the value predicted, and minimize that, like take like least squares, for example, solution, and find the minimum value, right? If you have a bunch of points and you want to draw a regression through them, well, you draw it, you calculate the distance, right? And you find the optimal sort of curve that optimizes the sum of all the distances, right? Well, you can do actually exactly the same thing here, and then the way you write it is you take the sum in between the labeled values and the predictor you want to do, and you want this to be the smallest, right, in the class of the functions that you're dealing with. But the difference is we also have a graph structure. And since we have a graph structure, we actually care about neighbors. So we want, on one hand, to have a sort of consistent mapping of the functions on the nodes that are labeled. But on the other hand, we want some sort of smooth solution. And so we remember that on the nearest neighbors, the values should not differ too much, because we don't expect our solution function to do like stuff like that. We want it to be more or less smooth. And so, which means we need to add, when we try to sort of solve for linear least squares, we need to add some sort of smoothness. And that smoothness can come from the following factor. Here is the values that on one node, that's the value on the other node. And if they're connected, right, we'll just make this functional. We calculate the value and we want this difference to be small, right? It's going to be small only for those that are connected, directly connected. You can also, like in a traditional fashion, you can also add regularization, which is you just, don't want to have very, very large values sort of in general. So you can use that factor. And pretty much regression on graphs combines all these things together, all these factors together, and builds the minimization process. For example, in fact, this random walk solution that we looked at, this label propagation, can actually be thought of, through the minimization of this functional with a random walk. One can show that minimizing this functional is equivalent to the random walk process we have described previously. Or there is a sort of traditional, what's called Laplacian regularization approach, where we look, first of all, at this Laplacian, right? So what we have here, this again, these are adjacent nodes, right? Where the graph connects them, and we just make sure that the values of the nodes, the value of the function on the adjacent nodes don't change a lot. And here we are adding up all the values on the labeled nodes and just make sure that what we predict on the labeled node is not far from what it is, from the actual value. Now notice, we're not requiring in our interpolation function, in our solution, to actually, for the value to match exactly the value of the label. There can be some difference. So it's in the same spirit as when we build regression. We're not requiring necessarily the function, the regressor, to go through all the nodes. We're kind of allowing it to go in between, because sometimes it's just impossible to satisfy it, right? And then, going through all the nodes will actually make things noisy and unstable. So, that approach is called Laplacian regularization, proposed by Belkin. And, to solve this, and the reason it's called Laplacian is because he proposed to solve it using eigenvectors from the smallest value of the graph Laplacian. And you remember, we talked about graph Laplacians when we talked about graph partitioning. So calculate the Laplacian for the graph, find any eigenvalues, eigenvectors, and look for, classifier for regressor for regression function as a linear combination of eigenvectors. So very, very similar to what we have previously looked at. So you're just looking for the solution of this regularization problem in the basis of eigenvalues and eigenvectors. Quite similar actually to what we did when we looked at differential equations a couple lectures ago. And so the algorithm, and it's quite popular algorithms. So what you do is you compute, again, diagonal matrix, right? And again, you need diagonal to just, to have a degrees of the matrices. Here you compute Laplacian. Then you solve, for Laplacian and compute eigenvectors. And then you solve a minimization problem, because remember, we're looking at the functional. You solve minimization problem for those eigenvectors by finding the coefficients that minimizing the functional. And those coefficients, then you write the solution as a linear combination of those coefficients and eigenvectors, right? And if it's a regression problem, you just use that combination. If it's classification problem, you can convert it into the sign the same way as we did when we worked with Laplacian matrices for graph partitioning. So that's That's the algorithm. Now, let me give you an example of label propagation algorithm, the one that we described at the beginning, and how it actually works on the real graph. This is again the small graph, the karate graph. Two type of labels, red and blue. It's sort of, by looking at this picture, you kind of know what to expect, right? Most likely the nodes that are behind blue nodes, these nodes will probably become blue, this probably will become red. The only question is how, these nodes, what color for those nodes the algorithm will create. So if I run this algorithm, that's what I get, right? So obviously those nodes that are connected only to blue nodes became dark blue, connected to red nodes became dark red, and those nodes that are in between, well, they got the sort of probability, sort of, this mixed up classes, right, in between this blue and red, based on a connectivity structure. Now, it's actually more interesting to see what happens when we have data like this, where you kind of, where there's no very clear separation, right? Because for all these algorithms, classification algorithms, regression algorithms, it's very easy to work on clean data, right? But when you have data that is sort of maybe not precisely consistent, not perfectly consistent, then the question is if an algorithm can handle it. And that's exactly the case why you don't want, sometimes labels to be fixed, but you might allow them to change a little bit. And so when you run this algorithm, that's what it does. So it kind of, it kind of makes, red dominate in this case. I guess it just happened because of this node 2 and 3, right? The whole thing got severely red. And to sum up, there are a bunch of references. There has been a lot of work on this domain. And again, the idea is that you can either sort of try to propagate values in sort of very naive, straightforward fashion based on the edges. You can try to encode the values of the edge of connectivity into the features and then use traditional machine learning algorithms, or you can look into this sort of semi-supervised learning approach, the one we discussed today, where we have, we use connectivity pattern. And for example, we looked into the random walk approach and then regularization approach on graphs. So that at least should give you some sort of some instruments to work on when you need to solve this type of problems. But again, in as many cases, it's better to have a baseline, and the baseline would be the most naive algorithm, which is, take the labels of the neighbor and average them out. And if the neighbor is not labeled, find the value for the unlabeled node and then propagate it, iteratively through the entire graph by doing literally the same iteration type of process. All right, and with that, we're done for today. Any questions?
Well, we got seminar today.
I'm sorry?
A seminar today.
I think so.
Okay.
Yes. Yes. All right. Well, guys, thank you very much and have a good rest of the week.